So this lecture will be about the Artin reciprocity law. It's quite a theorem. It is considered as a generalization of all classical reciprocity laws, like the quadratic law of reciprocity that you have studied earlier, as well as the cubic reciprocity and higher biquadratic reciprocity, higher reciprocities of laws of Eisenstein, and so on and so forth. Now, in the context of this theorem, let me review what we have already perhaps met. Let K be an algebraic number field. We introduced generalized ideals. So a generalized ideal is something of the form MF, M infinity, where MF is an ideal of O sub K, and M infinity is a subset of real embeddings of K. So for example, you have the ith conjugate, so these are real conjugates, so the conjugate fields, so K to Ki, these are the various conjugate fields. So we're going to look at alpha goes to the ith conjugate, and here these i's are some real embeddings that are contained in infinity. Now, in this setup, we have I of m, which is the collection of the group of fractional ideals, A of K, fractional ideals. Co-prime to M. And when I say co-prime to M, I really mean co-prime to M sub F. So this is a group. Sometimes we denote this by as I sub K. It's too small here. As I sub K of M to indicate the dependence on the field K. Inside here we have, of course, P sub M, the group of subgroup of principal fractional ideals, alpha congruent to 1 odd star M. What that means is alpha minus 1 is in the finite part, and alpha I is positive for all I in M infinity. So this is the notation we have. So this is the subgroup, and the quotient group. The quotient group I sub I of M quotient I of M modulo P sub M is called the Ray class group mod M. So you have this, and a subgroup H satisfying the condition that PM is contained in H, is contained in I of M. Such a group H is called a congruent subgroup. It's called congruence subgroup. congruent subgroups in general in algebraic groups, which is, of course, a generalization of this kind of idea. And we denote I of n modulo h is called a generalized ideal class. So this is the setup that we have. And for each ideal class, of such a group, C, of such a group, we can define a zeta function. We define the ideal class zeta function. As follows. Zeta SC is simply summation 1 over norm A in the S as A runs through all these ideals in this class. So I hope everybody is clear that when I take M to be the full ring of integers in this definition, so supposing I take M to be the full ring of integers and the M infinity to be the empty set, which I can do, then the ray class group is the classical ideal class group. And so these are generalizations of the ideal class groups. So you have this ideal class zeta function. Now, the analytic continuation and functional equation was quite an ordeal in the history with respect to these functions. Special cases of this, in the case of binary quadratic corresponding to binary quadratic form quadratic fields, was already done by Dirichlet to some extent. But the general theory of that was needed in order to study these zeta functions was developed in 1903 by Epstein. So what he did was he took a R by R matrix A over the reals, which is positive definite. Positive definite matrix. And he defined a zeta function, summation V in, so V is a vector with integer entries, and you look at the inner product A, B, B, and minus S, which is always positive, therefore there's no problem here. Of course, V should not be 0. This is called the Epstein zeta function. Epstein showed, using Poisson summation, some R-dimensional version, of course. R-dimensional version. That ZAS admits an analytic continuation for all S and C in the complex plane, except S equals 0, sorry, S equals 0, and S equals R over 2. Where it has a simple pole. and satisfies a very nice functional equation. Let CA of S to be pi to the minus S, gamma of S, gamma is the gamma function of course, ZAS. Then CAS is equal to a to the minus determinant of a to the power minus 1/2 C a the r over 2 minus s. A good place to study the Epstein zeta function in the English language is Siegel's lectures. So C. Siegel, Advanced Analytic Number Theory. TFR lecture notes. Study that. Now, one can transform the study of zeta SC into an Epstein zeta function and then apply this theory to derive the analytic continuation functional equation for these ideal class zeta functions. I'm not going to do it, but Cindy may have already explained in some tutorial or some lecture how that would be done. If you're seeing this for the first time, it may be a good idea just to have some outline and some basic examples in your mind so that you're convinced that the general theory should go through pretty well. So now what we do is just state the theorem for our purposes. So the fact is zeta SC extends to the entire complex plane except for a simple pole at S equals 1 where with the residue 2 to the R1, 2 pi to the R2, times the regulator R divided by W, square root the absolute value of the discriminant. So let me explain these quantities here, little k. So the d sub k is the discriminant of k, it could be negative, so we take the absolute value. W is the number of roots of unity in little k. R1 is the number of real embeddings, R2 is the number of, 2R2 is the number of complex embeddings, and capital R is a regulator, which is the determinant of a certain matrix using the generators for the unit, which I'll not get into. You can see my problems in algebraic number theory book for the explicit description of that. So we have this is the residue, and putting CSC to be e to the s, gamma s over 2 to the power r1, gamma s to the power r2, zeta sc, where a equals 2 to the minus r2 discriminant of k to the power 1/2 pi to the minus n over 2. Here n is the degree of the field over Q. So this is the function CSC, that the functional equation, the functional equation takes the form zeta SC is equal to, CSC is equal to C of 1 minus S C prime, where C prime turns out to be equal to the inverse different times the inverse class. So this is D is the inverse different. Remember, as I said, if you look at my problems book in algebraic number theory, I discussed the different ideal. The different ideal is an ideal of the number field K whose norm is equal to the discriminant, whose absolute norm is equal to the absolute value of the discriminant. So that's an invariant that keeps coming up in many of these calculations. So you have this nice functional equation. Also, you can see page 254 of mine. And as I said, the secret in deriving these things is firstly understanding some basic algebraic number theory of structure of rings of integers of number fields and so on and so forth. And secondly, to apply the Poisson summation formula to get that. Now the interesting thing is Weber introduced these zeta functions. So he's the first person to have introduced them. Weber introduced these ideal class zeta functions. He didn't have all this stuff. So I think Weber's work is in late 19th century. We're talking, Epstein's work is early 20th century, so it's a time gap. So he didn't have all these wonderful properties of the zeta functions. So when he introduced them, he was keen on proving an extension of Dirichlet's theorem of primes and infinitude of primes in arithmetic progression. So the analog of the infinitude of primes in arithmetic progressions in the number field context turns out to be infinitude of prime ideals in a given generalized ideal class. This is a very key point. When you study the ideal function, of course, you should understand that somehow ideal classes or generalized ideal classes are the generalization to the number field context of the notion of an arithmetic progression. That is the, I think, the winning, idea of the 19th century algebraic number theory. It's a very, very important idea. So the L function, so given a character of this one of these generalized ideal class groups, given a character, like a homomorphism character, we define LS chi where A runs through the A runs through over all ideals, non-zero ideals. Okay. Now, this only depends on the ideal class that it belongs to, so we can partition this and write it as chi of C, where sum over ideal classes of this group times the ideal class zeta function. So because we know the ideal class zeta function extends to an entire function, extends to an analytic function except for a pole of s equals 1, we immediately get analytic continuation of LS chi from these objects. It's a finite sum. And remember, the ideal class groups have finite order. This is something that Cynthia already covered, the order of the things. Okay. So we know it's a finite sum, so when you add a finite number of analytic functions, you get an analytic function. The only problem point, of course, here is that s equals 1, but then the residue, as you can see, the residue is the same here. The residue, it does not depend on the ideal class. Therefore, when you look at the sum, the residue comes outside, and summation chi of C is 0 if chi is a non-trivial character. Therefore, there's no pole if chi is non-trivial. So LS chi, if chi is non-trivial character, LS chi extends to an entire function. And using the functional equation of CSC here, you can paste the appropriate nice functional equation for LS chi. Satisfy the suitable functional equation. Okay, suitable. I'm not going to write it down. Relating LS chi to L1 minus S chi bar. Let's see, functional equation. I mean, there's a bunch of gamma factors and all that. I'm not going to put them all in, but you can see how that'll work. So you get this. This is something that Weber didn't have. So he managed to squeeze some sort of analytic continuation for a real part S greater than or equal to 1 and tried to argue from there. And he got stuck. And he wanted to mimic Dirichlet's proof of the infinitude of primes in arithmetic progressions. Therefore, he was motivated to postulate the existence of some Galois extension where this thing becomes a factor. So with the goal of extending Dirichlet's theorem, to generalized ideal class groups, Weber postulated, and this is an important step, Weber postulated the existence of an abelian extension capital K or little k such that the Dedekind zeta function of the capital field K equals product of these ideal class zeta functions. So chi is a character of these ideal class zeta functions, ideal class groups. So something like this. And then using the non-negativity of the coefficients here and using the fact that the Dedekind zeta function doesn't vanish on the line at S equals 1, you can now see if L1 chi were 0, it'll cancel the pole coming from the trivial character, and then you would get some finite number here. But at S equals 1, this has a pole, therefore there's a contradiction. So that's basically how he finished the proof and proved his theorem. So he postulated the existence of this thing, and then showed infinitude of prime ideals in a given generalized ideal class. So this board is kind of funny. Generalized ideal class. Okay. So far so good, but now with the hindsight of more than a century, it is clear that there was no need to make this postulate. You can prove the infinitude of prime ideals in a generalized ideal class without making this assumption. And we know that because thanks to a theorem of Landau. Thanks to the theorem of Landau. After more than a century, we see the theorem can be derived without this hypothesis. Landau's theorem, which was proved in the early 1920s. Maybe it was proved a little earlier, but certainly in the 20th century theorem. Landau's theorem. So what does this theorem say? It says that if you have a Dirichlet series with non-negative coefficients, real coefficients, non-negative, and it's a Dirichlet series, and then there's something called the abscissa of convergence of the Dirichlet series. That is the point on the real line to the right of which the Dirichlet series converges, and to the left of which, of course, the series diverges. So that's a typical, critical point. It's called the abscissa of convergence. If f of s is this, say, converges, absolute converges for real part s bigger than 1, and admits let me just say it like this, scrap all this. If f of s is that with a and non-negative, then f of s has a singularity that is abscissa. Now, in our situation, instead of saying that the Dedekind zeta function of some hypothetical field is actually the product of these LS chi's, instead of saying that, just consider this product over these characters. We call this guy f of s. Then, small exercise to show that this f of s is a Dirichlet series with non-negative coefficients. The ends are not negative. And so Landau's theorem immediately tells you that this has a singularity, it's abscissa of convergence. Now, if L1 chi were equal to 0, since for the trivial character there's a pole, that L1 chi being 0 cancels the pole, and we finish showing that there's only one problem point s equals 1, therefore this is actually an entire function. If L1 chi equals 0 for some chi, then f of s is entire. Which means, but this theorem says that it has to have a singularity at the abscissa of convergence. Therefore, the Dirichlet series converges for all values of s. Hence, by Landau's theorem, f of s converges. The series converges, the Dirichlet series. Already that this is a kind of a contradiction. If you grant me for a moment that a sub n's are at least, well, infinitely often they're at least 1, suppose. If you grant that a sub n's are at least bigger than, or strictly positive, bigger than some constant c for infinitely many n, when I plug in s equals 0, it's already a contradiction. But there's a small argument that you can make if you don't want to make that hypothesis. You can actually show that that this actually is a contradiction. Small exercise shows. A moment's reflection, I guess. Small exercise shows this is a contradiction. So I'll leave it with that. So there's, this is a historical point perhaps. People were of the view you needed all this remarkable construction of class field theory in order to show this, but you really don't. In retrospect, Landau's theorem is enough. But in the meanwhile, as I said, there were several things that were having parallel development in number theory. One was the theory of zeta functions, along with complex analysis, trying to understand the analytic nature of these functions. And the other was the algebraic side, where we're trying to figure out and develop what are the generalizations of the Riemann zeta functions and Dirichlet L functions. That's what's going on here. That's the motivation. Now, we will apply our theorem to the cosmos subgroups P sub m times this norm capital K. So this is a group that I'm going to define. So this group. So here the picture is, here's my field little k, and here's some, well, it could be for the time being any field, any finite extension for now. It doesn't have to be finite extension. It doesn't have to be necessarily. So this group here is the collection, is a group of norms, norm, capital K, little k, of ideals, A. A is going to be co-prime to M. That's it. So it's a group of all norms of fractional ideals, all these fractional ideals, which are co-prime to M. We just take these, this is called the norm group. The norm group. So it's a relative norm. So when you take the relative norm, it's an ideal in the base field K. And so you look at this. This, of course, is contains Pm, and of course it's contained I. And notation, we have that. And when we look at when we look at the consequence of this, that here, I want to see how it relates to this study of this group. So one consequence is that if I look at the Analytic zeta function, so consider this is a kind of a remark independent of all this context, but I need to recall this fact. So recall that this has an Euler product over prime ideals, 1 minus 1 norm ADS. So that when I take the log of the Analytic zeta function, that's equal to minus and using the expansion minus log 1 minus x as summation x to the n over n. Using this back in calculus, you see that this is equal to summation n 1 over n norm p to the ns. Separating the term n equals 1, and bigger than or equal to 2, you can see that the sum corresponding for n little n bigger than or equal to 2 gives rise to a function which is analytic to the right of a half. So I'm going to denote this as all sub 1/2 plus s. So this notation means this is an analytic for real part s bigger than a half. It's some analytic, I don't care what it is, some analytic function, okay? So I'm going to focus my attention on this, and because the Dedekind zeta function has a simple pole of s equals 1, you can see that this behaves like log of 1 over s minus 1, and if capital K over little k is a Galois extension, unfortunately I'm using, so I'm not consistent with my notation. If you don't mind, I'm just going to change these to script P, because this is script P's. Because these are script P's are prime ideals upstairs, and I want to use German P's for prime ideals downstairs. So that's clear. So you know that if I have a Galois extension and I have a prime ideal downstairs, P here, it will break up into a bunch of prime ideals upstairs, P1, P, G. And we say that P splits completely in K if, basically, if G equals the degree of this. In other words, what's the largest number of prime ideal factors you can have? So if it splits completely, the number of prime ideal factors is the maximum you can possibly have. So that's the, so if this means that if P splits completely, they're exactly n prime ideals above the thing with n as the degree, that is. So you have this. Now in this sum here, we can separate out those prime ideals when they split completely. By the way, notice in this case, the norm of script P, script Pi, is the relative norm. The relative norm is the prime ideal. Therefore, if I can separate out those primes P that split completely, and of course these are absolute norms here. This is the absolute norm. So that's the same as the absolute norm of this. See, the norm of so therefore, this is actually 1 over norm. Okay, it's the same thing. And every time we get one of those, you're going to get, so for each, you get this, how many times? You get it as many as the degree of the field. So you get K over Q, capital K over little k, the degree, and therefore you get this theorem. If capital K over little k is Galois, finite extension, then the density split density of the set split capital K over little k is the collection of prime ideals, German P, that's split completely in capital K. That set has, the density is 1 over the degree of the field. It's 1 over. Space here. So in particular, we have this following corollary. If capital K does not equal little k, then there are infinitely many prime ideals. Which do not split completely in capital K. Now this is an interesting thing because I don't know how to prove this without using analysis or theory of zeta function. What I do know how to do without using any zeta function idea is to show that there are infinitely many primes that split completely. That I can do. That's actually quite elementary. You can do that using polynomials, prime divides polynomials, but you can't the other way, as far as I'm aware. This is the only way to get at this result. Good. Now, an important part of this is to observe. Let's just push this down a bit. Observe that in this set, split capital K over little k, we have all the prime ideals of little k, which split completely. If that's the case, all those prime ideals we see from this remark here that norm capital K over little k of script P is German P. Therefore, each of these prime ideals is a relative norm of a prime ideal upstairs in those cases. Therefore, it's clear to you that from our discussion, we see that the collection of primes that completely contains the normal where M is divisible by the ramified, the primes, prime ideals of little k, which ramify in capital K. So, hope everybody understands this. The observation that when a prime splits completely, the prime ideal P is actually a relative normal of a prime ideal upstairs allows me to make this inclusion. Therefore, the Dirichlet density, or the density of prime ideals of this set, has to be smaller than the density of primes of this set. Now, by our notation, I can shove in here P sub m, because they've always contained the identity. P sub m is the fractional ideals, co-prime to m, satisfying that congruence condition, right? So this containment is of course there. And so let's call this group H, as we did earlier. And we see that prime ideals that belong to this particular H, the density of prime ideals that belong to this thing is larger than the split primes, right? Therefore, now we know from our, I should have pointed that out. So they're not only, you know, from Weber's work, or this comment that I made with respect to Landau's theorem, we know that L1 chi is not zero. Therefore, the density of prime ideals in any given ideal class is the expected density. It's 1 over the order of the generalized ideal class group. So we know, so we're trying to ask how many prime ideals are there in this particular class. Remember, the generalized ideal class group is I of M modulo H. That's our generalized ideal class group. The class H is the identity class in this group. Right? These are cosets. So the coset H, the subgroup H is the identity coset, or right. Therefore, the collection of prime ideals in this class has density 1 over the order of the group. We know the density of prime ideals in the H, belonging to H, is 1 over the order of this generalized ideal class group. So the density of prime ideals in this set is this number, and the density of prime ideals in this set is 1 over the degree. Therefore, we get an inequality. So we get what's called the universal norm index inequality. Which is that this is true for any Galois extension. So we get this universal norm index inequality just by comparing density of ideals. Now, the work of Takagi goes back to the 1920s. And he asked himself the question, is this sharp? Wait, is it a strict inequality? Always. And so he shows that there exists M naught such that we have equality. And in a field K, there exists M naught and a field K such that we have so let me use C naught because I know you use C later. This is C naught. And a K, abelian. K abelian over little k. K over little k abelian, finite abelian extension, such that this is actually equal to inequality. So so this is not a strict inequality always. Can't get bigger than that, but it can actually equal that. And that's an important theorem. This theorem is an important theorem. It is beginning of Galois cohomology. In essence, what Takagi was doing in his papers was studying the action of the Galois group on the ideal class groups, and he was studying the action of the Galois group on the unit groups, and seeing what are the implications for this inequality. And he finds that if you choose your M sufficiently large, in the sense of it's divisible by all the ramified prime ideals, and after a sufficiently large ideal, then it turns out that this holds. So this is what's called the universal norm equality. This is, by the way, I think somebody has a copy. Well, okay, you have a copy of Lang, but I think in Lang, at the critical moment in the proof of the reciprocity law, he refers to this as the universal norm inequality, and this is not right. So this is universal norm equality. Which is where we would start the proof of the reciprocity law. So this part, I'm going to assume that there is a C naught and indicate how the proof of the Artin reciprocity works. All right. So in order to talk about the Artin reciprocity law, we need to discuss the Artin symbol. So, just to recapitulate, so I have a finite Galois extension. We agreed that we have a bunch of prime ideals upstairs, like so, and the ideal generated by the upstairs factors. For each prime ideal upstairs, we have what's called a decomposition group. Collection of automorphisms of the Galois group. So let's give a name to this Galois. G is Galois capital K over K. So sigma is in G, except that sigma of P is P. So it fixes that. And inside, so PI. So okay, that's from. So you have that, and then you have the what's called the inertia group, which is sigma x. Sigma x is congruent to x modulo p for all x in the ring of integers of capital K. And the inertia group is a normal subgroup of the decomposition group. And the quotient is a cyclic group. Which can be identified canonically isomorphic to the Galois group of the ring of integers of OK modulo P, thought of, which is a finite field, thought of as a finite field extension of OK modulo of German P. And we know that this is a cyclic group generated by what's called Frobenius map for Oslo's theorem. So x goes to x to the norm P, that's the map. And so the Frobenius automorphism, so these guys are sitting inside the Galois group, so there's a unique element modulo the inertia group. Sigma sub P, call it. There exists a unique modulo, of course, inertia. Call it sigma sub P, which has the same effect. Sigma P acting on x is the same as x to the norm P modulo P for all x in the Riemann closures. So there exists this automorphism, and this automorphism is called the Frobenius automorphism. And as we look at a prime ideal P here, and we look at the sigma P's that correspond to the prime ideals upstairs, they turn out to be conjugate. And the conjugacy class of sigma P is what's called the Artin symbol. This is designated in several ways in the literature. Sometimes people use designated as sigma P, like so, or, as I will do in this particular talk, sometimes it is useful to have the dependence of the field that I'm talking about in the picture, because there's a certain functoriality of this symbol that will play an important role in the proof of the reciprocity law. So, now, if the field extension is abelian, so let's keep that marking. If capital K over little k is abelian, then sigma P, the Artin symbol, was well defined up to inertia, so let's not worry about those ramified prime ideals. Sigma P is actually an element of the group. Okay. So we have a well-defined group element for every prime ideal P. All right. So now, what do I want to do? I want to study the what's called the Artin map. Thus, if capital K over little k is abelian, we have a well-defined map. We have a well-defined map for prime ideals P of close to K, P unramified in capital K. We have a well-defined map from the set into the Galois group. So we can extend this map to the collection of all fractional ideals co-prime to the different of K. So if I take a collection of ideals which are kind of co-prime, I have this Artin map into the Galois. Given by, give me an ideal A and I map it to product of so here I'm writing my ideal A as a product of prime ideals like so. And so I have this nice map. Sometimes this map, this element here, is denoted as sigma A, or the element A, capital K. So this is our notation. So we have well-defined map. All right. Now, the proof of the reciprocity law can take quite a bit of time. So what I'm going to do is I'm just going to give you the outline, main steps, and you can spend a lifetime studying this, but you can spend a week or two, perhaps, studying the details in Lang's book. So we have this map, and so the first statement that we'd like to make is that this map is surjective to theorem. So this is often called the Artin map. The Artin map, the map G is surjective. So the proof is nice because it uses what we just finished proving. So suppose not. Suppose H is the image of the Artin map. Then so let's draw a picture here, K. So let's look at the fixed field of K, of H. So we have this. So here's the Galois group is G. Now let's keep in mind in this definition of our Artin symbol. When is this symbol 1? Well, that means it's the identity element. It's the identity element if P splits completely. So if P splits completely, you have the full, you have the maximal number of prime ideals above that thing. So the Artin symbol is trivial. Note. If and only if P splits completely. Okay. So what does it mean that if the Artin symbol also has another important property. So let's point that out. If I take the Artin symbol, has this nice functorial property, restricted to subfield KH. This symbol is nothing but that. It's the functorial property. Okay. So if I'm looking for but I know that the Artin symbol restricted to this field is trivial. That's the H acts trivially on this base field. It's a fixed field H, right? So H is acting trivially. Therefore, if all the Artin symbols are acting trivially, that means every prime splits completely in KH. Every prime of little k splits completely here. But we proved that, we proved that if capital K is not equal to little k, they're infinitely many terms that do not split completely. Therefore, the only way this can make sense is if kh is actually equal to k. Okay, so that's the proof. So we now know that the image of the Artin map has to be the full Galois group. By Galois theory, it has to be the full Galois group, because you can't have a proper extension. A very beautiful thing. This is a combination of algebraic number theory and group theory, and this functorial property of the Artin symbol, which is very interesting, Galois theory. So when I say group theory, I really mean Galois theory. So you have that. So we now know that the Artin map is projected. What is the kernel? What is the kernel of the Artin map? Well, the Artin reciprocity says, Artin's theorem, is that there exists a generalized ideal C such that the kernel such that is isomorphic to the Galois. So the kernel of the map is one of these congruent subgroups that we defined. So that's the kernel. And therefore, not only that, the isomorphism is not an abstract isomorphism, it's the isomorphism given by the Artin symbol. That is, the ideal A goes to the Artin symbol. That's the isomorphism. So it's an explicit theorem. All right. Now, how does one prove this? Okay, let me try to outline the steps of the proof. Is it about 20 minutes? Okay. So outline of proof. The first part of the proof actually is very simple and proceeds by trying to understand the functoriality of the Artin symbol. You see, I think it's interesting to make this kind of historical remark. It's interesting that all of this, the evolution of class field theory, is responsible for several streams of thought in the development of 20th century mathematics. First is, of course, Galois cohomology, as I just outlined in the paper of Takagi, when he was trying to show that there exists a cycle where you have some equality. He was essentially playing around with Galois action, and they formalized it into Galois cohomology. That's basically Artin Tate class field theory lecture notes. And Herbron saw that actually the argument of Takagi rests on a simple group theoretic property, and he tried to formalize that so that you have this Herbron quotient machine. So when people see that without any motivation, you find that it kind of jars up on your years, perhaps, the best thing is to go to Takagi's paper. Unfortunately, it's written in German, Takagi paper. So try to rummage through that and see what the ideas are, and then you find that very interesting evolution of ideas. So let me kind of recapitulate a few basic properties of the Artin symbol. So if you have a field K prime which contains K, which contains little k, or abelian extensions, then the Artin symbol that I would define for an ideal A of this large extension, keeping in mind the Artin symbol is always a Galois, an element of the Galois group. So if I take that and I restrict this to capital K, we already use this property, I think. That's equal to K. This is what's called the consistency And if I have if I have a bunch of fields, so take little k here and capital K and E, and suppose they intersect in a field capital K intersect E, an extension of little k, and look at the positive. So, as I mentioned, these theorems are easily proved just by going to the definition of the Artin symbol. It's very easy. So if I have a prime ideal Q above P, so P is sitting here, you have this prime ideal Q, then let's say the norm of E over K of this prime ideal Q is P to the F. Then the Artin symbol Q KE over E, so keep in mind KE over E is this extension. I've got this prime ideal Q here, and I compute the Artin symbol here, keeping in mind that the Artin symbol will always be some sort of element of the Galois group. So this guy is the same as P to the F, capital K, little k, where P to the F is the norm, E. So this is very elementary. And then as a consequence of this, by multiplicativity, we get that if you give me an ideal B, KE over E, this is the same as the norm And so as a consequence, and this is just a consequence of 2, as a consequence of 3 now, if capital K contains little e, capital E contains little k, then the Artin symbol B K over E is the same as so in particular, if little e, capital E equals k, in particular, if capital E equals k, then 1 equals the norm, the Artin symbol of the norm of capital K, little k, of other words, all the norms of ideals are in the kernel. Very important property. So all the norms of ideals, which are co-prime to the different, are contained in the kernel of the Artin map. So, i.e., with our notation, the norm group from K to K of ideals co-prime to different is contained in the kernel of the Artin map. Okay. Now, so what Artin does in the proof of the reciprocity law, what he does, maybe I should move to that board. So there are several observations to make. So the proof of reciprocity. Begin with that cycle that Takagi produced. So let's C naught be the generalized ideal such that we have equality. Begin there. Take that out. Then step one, the reciprocity law holds for Q zeta M Q. What is the generalized ideal class group that you need to deal with here? Well, I think Cynthia already points out in her thing that you need to take M infinity, where if you include embedding, the usual embedding. This is the ideal you need to take, and the generalized ideal class group modulo this turns out to be Z mod MZ star. So that's the classical situation. Step two is the reciprocity holds for other subatomic fields. If M is unramified, M is co-prime to all the ramified prime ideals. Now, the proof of this is, I'm not going to do it because I think I'm running out of time, but the proof of this is just this symbol chasing, as I call it. So you just look at how does this work. Well, you go back to this kind of picture where you're going to, so you're going to look at the cyclotomic field and maybe you join some, you have another extension, you would join the nth root of unity and follow that through, and that gives you the result. Step 3. So I think it's plausible. You can believe that this actually extends. Once you know the mechanics of the Artin symbol, you can extend the reciprocity law to any relative cyclotomic extension. Right. Step 3. If A divides the ideal B, then I of B modulo p sub B norm B, the natural map is surjective. So this is saying the following: if I have let's say in the elementary number theory, what you have, if you have a divisor D dividing n, and I have residue classes modulo n, right? I can reduce them modulo D. Right? So you take a residue class modulo n, D is a divisor of n, so I can continue, and that's a surjective map. So the residue classes modulo D lift to residue classes. So this is a surjective map. So now, the point is that let C naught be as in step 0. I should have called this step 0. Let C naught be as in step 0. Then what do we have? But if C naught divides, then by this remark, by step 3, we have a surjective map. So I of C modulo P sub C norm C modulo the kernel of this map. Let's call this psi, this natural map. Kernel of psi is isomorphic to I of C naught And now the point is that we know that this quotient has cardinality equal to the degree of the extension. Therefore, this has to have cardinality equal to it. But then this guy here is at most the degree of the extension. Therefore, the kernel has to return. By the universal norm index inequality, we see kernel psi equals 1. And therefore, this means that the therefore, the kernel of the Artin map, hence, the kernel of the Artin map, so we'll call this by Artin. This is the Artin map. I don't think I gave a name, but it's basically the map that takes the ideal to the Artin symbol. The kernel of the Artin map is contained in, remember the Artin map went from some IFC to the Galois group, so the kernel of the Artin map is contained in P sub C. For any C that's divisible by the C naught after that point, right? So we have that, and sorry. So sorry, this is not quite correct. So if we can show, if we can show this, that there exists a C such that C naught divides C, and this happens, then by our observation here, y star, kernel of the Artin map actually has to equal. So which is basically what I'm trying to say with respect to Artin's theorem, that there exists a C such that this happens. And so now the point is we've reduced the question to this situation, and there are a few more steps. A few steps, let me just try to indicate how they are and then stop. So that was, I think, step 3 there. This should have been step 4. And step 5 is basically to say that suppose we have an element in the kernel and we write our ideal A as a product of prime ideals Pi to the Vi, I going from 1 to R distinct prime ideals. And we want to first study the cyclic case. First study the case capital K over little k is cyclic. So you see you have this abelian extension, you have this Artin map surjective, you're trying to produce a cycle. So I'm going to start by assuming this capital K over little k is cyclic, and then prove that there exists a cycle C which works. And then because every abelian extension is a direct product of compositum of cyclic extensions, one can finesse this proof to do the arbitrary abelian case. So we can assume that we have a cyclic situation, and so the Galois group is generated by some element sigma say. And therefore, these Artin symbols, each Pi K over K. So write each of these guys as sigma to the di. So you know it's a power of sigma. And because the extension has degree n, to say that the Artin symbol is 1, implies that summation di from I going from 1 to R must be a multiple of n, dn, for some d. Therefore, n divides the sum of the di's. Now that E, so there's a little bunch of elements of elementary number theory, so let me just introduce that here as F6. Elementary number theory dealing with prime divisors of cyclotomic polynomials. And out of that, so this is very elementary number theory, out of that you get what's called Artin's lemma, which allows you to construct an extension. Let me write that down. Lemma says that let K be a number field. Capital K, little k, finite cyclic extension. S, a finite set of primes. Then there exists an integer m, co-prime to S. That means co-prime to all these primes in S, such that one K, sorry, there exists an M and an extension E such that K intersect E is little k, 2 K adjoint zeta M equals E adjoint zeta M. And capital K intersect K zeta M is little k. 3, P splits completely. Oh, sorry, I should have said something here. Let K be a number field, capital K over finite cyclic extension. P a prime, I give it a prime idea, P a prime of K. So you give me that. Then I can arrange for these things to happen. Splits completely in E. So let me just draw a picture here. So you have your field K, little k, you have your capital K, you have this field, I'm saying this field E exists such that basically this is KE and it's K zeta M picture. Now, what am I trying to say? I'm trying to say that this Artin's lemma is a consequence of the elementary number theory that goes in here. So this elementary number theory about the prime divided cyclotomic polynomials, and understanding cyclotomic theory allows you to arrange for this. And once you have this Artin lemma, what you have to do is you have to go back to the condition that we had, analyze when can this happen, using the construction of these auxiliary fields, one for each of these i's actually. Construct these auxiliary fields, using the functoriality of the Artin symbol, conclude that the ideal that you started with here, the ideal that you started with, which was in the kernel, is actually an element of this this compound. So that's basically the proof. So the proof is a little long. However, I hope I have convinced you that the proof is within the understanding of a smart undergraduate in the following sense. That there is firstly sort of the elementary number theory argument in here. Secondly, that there is the functoriality of the Artin symbol, understanding basic Galois theory and how these things relate. The only magical element that I would say catches you off guard in this proof is really step 0. Step 0 is that step from Takagi's paper where there's a divisor or ideal such that you have equality in the universal norm index inequality. That's all. And that is the part where the discussion with respect to cohomology comes in. And since the lectures on the norm index inequalities are done by Kumar in his lectures, I'm assuming that perhaps that step will be discussed in a little bit more detail in his paper. How much time do I have?
137.
Oh, okay. So I'll just say a few words.
Could we end on the last board?
Oh, you mean this one? Do you want me to push this up?
It was actually at the top.
Pardon me? You mean all the way to the...
Oh, no.
This one? Okay, oh, sorry, yeah. Sorry, I didn't realize that you didn't finish. Okay, yeah. So we have that. I think that that should be enough for studying the reciprocity law. So one of the things that the reciprocity law allows you to do is, of course, say that the abelian Artin L function is actually an ideal class L function. And that is a theorem we'll use in our next talk where we discuss consequences of Artin L series and Chomtar density theory. Yeah. Okay, so